Hi everybody. I wanted to go through in this video the worksheet that I have posted for you called Determining Aromaticity. This is designed to go along with the first chapter on aromatic structures in our organic chemistry class. So what I've done here is I've taken 3 problems out of the textbook, and these are taken from the Klein Organic Chemistry textbook, that all 3 address the idea of aromaticity in kind of slightly different ways. So problem 1730 here, the first one, asks us to identify the number of pi electrons in each of the following compounds. And that's a key component towards determining aromaticity, because remember, aromaticity says that we have to have 3 criteria fulfilled. We have to have a ring structure of some kind so that we can get that cyclic delocalization. We have to have a flat structure so that all of the unused p, or all of the p orbitals, overlap one another, allowing delocalization. And so for the most part that requires sp2 hybridized atoms all the way around. And we have to have that magical number of pi electrons. And remember that formula is 4n plus 2, where n is any integer. So we're talking about numbers like 6, 10, 14 pi electrons. We have to determine those first. So this first question, 1730, asks us to do that pi electron counting. And so when we look at problem A here in the text, we obviously see a number of double bonds. Well, those will contribute to the pi system, right? All of those carbons are sp2 hybridized, and so the extra electrons are in the pi system. And so we have 2, another 2, another 2, another 2. Then the question, of course, is what about this lone pair of electrons? So we want to think about what is the hybridization of that carbon. And don't forget its 4th pair of electrons. It must have 4. So there is a hydrogen on there. And this is one of our opportunities to talk about hybridization. We can say, ordinarily, an atom that has 3 bonds and a lone pair of electrons, or any 4 groups of electrons, we would say that atom is going to be sp3 hybridized. However, in this case, notice that if it is sp2 hybridized, with that lone pair of electrons occupying a p orbital, then we can say we have that special extra stable, energetically favored aromatic condition. And in fact, that's true. This carbon, in this particular scenario, will adopt an sp2 hybridized format, whereby the 3 single bonds make up the trigonal planar structure, allowing that pair of p, that lone pair of electrons. I don't know what is happening with my markup here. It does not want to work. Try this again. My Apple Pencil is not working for me. That is great for a demonstration. See if we can sync it up. Anyway, making that extra pair of electrons flow into the p orbital, become part of the pi system. And by doing so, that gives us now 10, there we go, 2 more. That gives us 10 pi electrons, which is one of the Huckel numbers. This is an aromatic molecule, or ion, I guess, in this case. So that's going to be kind of our rule of thumb as we go forward, is to say what geometry would you expect, and then is there any other geometry that would be better than that? And so we'll see that a couple more times and we'll talk about it. Part B is another example here. We've got, zoom in on this, 2 pi electrons for each of the double bonds. That's 4. Again, we look at the sulfur up there at the top and we say, what's its hybridization? Ordinarily, we would say sp3 hybridized, 4 groups of electrons around it. However, in this case, if one of those pairs of electrons was in a p orbital, that would give us 6 pi electrons. And that's an aromatic molecule. And so that is, in fact, what happens. We have those electrons will be in a p orbital to be part of the pi system, whereas the other pair of electrons would be in an sp2 hybrid orbital for that atom. Okay, so 6 pi electrons. Next molecule over here, part C, we've got a whole bunch of stuff going on, but obviously double bonds, 2 electrons apiece, those are all in the pi system, and there's nothing else, right? Both of the carbons up at the top here have hidden hydrogens, those are both sp3 hybridized, and so all we've got are the 10 pi electrons that are shown. So we look at part D, we get another heteroatom, so we need to think about what this heteroatom is doing. So we do have our 2 pi electrons from the double bond, that's fair enough. Now we have to think about the nitrogen. Here's a case where the heteroatom is already participating in a double bond that involves its p orbital. So the lone pair that we have off to the side must be in an sp2 hybridized orbital. So those lone pair of electrons don't count towards our pi electron count. We have 2 electrons in each of 2 double bonds. That gives us 4 pi electrons. Then over here, this positively charged ion, we would go through and we'd say I've got 2 pi electrons in each one of those double bonds. What does the positive charge mean at the top? Well, that means that we have a lack of electrons, right? There is no lone pair of electrons there to consider. We do have a hydrogen atom that is not shown in the skeletal structure, but that doesn't influence anything. Hydrogen can't participate in that kind of a bonding, or can't donate to a pi system. It's too small. So we have here 6 pi electrons. So those 5 structures ask us to sort of determine the number of pi electrons, which is an important part of our definition of aromaticity. If we go on to our next page, or on the actual worksheet, it was just the second question, 1732 out of the text. Now they're asking us to go one step further, not only to determine how many pi electrons we have, which we will have to do, but also to consider those other 2 factors. And so remember, we have to have a ring shape, we have to have a flat structure, which generally speaking means we have to have sp2 hybridized atoms. And 3, we have to have 4n plus 2 pi electrons. So first, we may as well look at our pi electrons. Okay, the first molecule, part A, has 2, 4, 6, 8, 10 pi electrons, which does satisfy the 4n plus 2 rule. All of the atoms here are sp2 hybridized, so it is flat, and obviously it is a pair of ring shapes. In fact, both of these rings, or each of these rings, is aromatic, and so in total, this molecule is aromatic. In this case, we only need one of the rings to be aromatic to consider the entire molecule to be aromatic. So this one happens that both rings are aromatic, but that's really not necessary. If we didn't have these other 2 double bonds, we would still call it aromatic based on the left ring. Okay, but we do, so we'll put those back. Part B, at first glance, might look kind of the same. We've got 10 pi electrons again, but this one is discussed specifically as an example. Molecules like this, which are really big rings, are called annulenes. And they're typically named with a number out front, so this one would be 10 annulene to indicate that there's 10 atoms in this ring structure. The thing we want to remember is that there are hydrogen atoms sticking out here on the inside. It's different to the molecule we just looked at, because in that first molecule, those 2 kind of middle, if you want to say, middle carbon atoms were connected together. They were bonded together. Which held that ring into a rigid structure. In this case, those hydrogen atoms will conflict with one another. They take up space. There's a little bit of steric interference. And so because of that, this sort of, I guess we'll make it red for drama here, this sort of steric interference, that means that this molecule is not flat. It cannot adopt a perfectly flat structure. So although all the atoms are sp2 hybridized and we do have the right number of electrons, the middle part of the ring will not permit the p orbitals to overlap all the way around. So we would likely see some conjugation from, kind of the ends of the molecule, but not aromatic. So not aromatic. All right. Parts C and D ask us to get back to heteroatoms. And in particular, we have to start thinking about these again. Where are the extra electrons? What's going on? I would encourage you when you're doing these problems to always draw the extra pairs of electrons where they belong. So nitrogen, oxygen, sulfur, whatever atoms are in there, you'll want to draw those in. So this is a great example of playing a what-if game. Now, we know that typically those oxygens would be considered to be sp3 hybridized with 4 separate groups of electrons. We'd say sp3 hybridized. And what I'm going to do here is say if the oxygens were all sp3, then we would have a case that we would say is just not aromatic, right? Because it wouldn't be flat. We wouldn't have overlapping p orbitals. However, we've seen before that sometimes we can consider heteroatoms to be sp2 hybridized if it benefits us. So if we get an energy savings, if we get aromaticity. And so let's think about that. If all the oxygens are sp2, that's the only way we could possibly have an aromatic molecule here. They'd all have to be sp2 because then we would have a flat molecule where the p orbitals overlap. So let's imagine that. If all the oxygens are sp2, that would mean that each oxygen would have a pair of electrons contributing to the pi system and a pair of electrons in a hybrid orbital. So pi system, hybrid orbital, pi system, hybrid orbital. Okay? And so what that is going to mean for us is that we can count up our electrons. If that's the case, and that's the only way that we could possibly have aromatic behavior, how many pi electrons would we have? Well, we'd have the 2 from the double bond right here. Let's go ahead and pick a nice color, okay? So we'd have the 2 from the double bond right there. We would have 2 more there, and 2 more there, and 2 more there. 2, 4, 6, 8 pi electrons. Well, remember, in order to be aromatic, we have to have 4n plus 2 electrons. But if we just have 4n electrons, which 8 would count, right? 4 times 2 is 8. If we just have 4n electrons, that would be that specially unstable case that we call anti-aromatic. So think about it this way. We have 2 options. If any of the oxygens are sp3, it's just not aromatic. If all the oxygens are sp2, it's especially unstable. Well, that's not going to happen, right? We're not going to have an especially unstable molecule. The more favorable case is to say that at least one of the oxygens will adopt an sp3 hybridized configuration, giving us the preferred state here of just not being aromatic. It's the lesser of 2 evils, the lower energy case. All right, let's look at D. Again, I'm going to draw on my lone pairs of electrons that are missing from the picture. Almost always missing from the picture for heteroatoms. Now we can look at this. We say the nitrogen is already sp2 hybridized, right? We have our p orbital overlap in the form of that double bond. And so our nitrogen lone pair of electrons are in a hybrid orbital. Now in order for this, the same as before, the same logic, in order for this to be flat, to be have any shot at being aromatic, the oxygen would have to be sp2 hybridized. And if that's true, then we would have 1 pair of electrons in a hybrid orbital and 1 pair of electrons in the pi system. So if that is the case, then what do we have available to us? Well, we've got 2 pi electrons there, 2 more pi electrons there in the second double bond, and 2 more pi electrons here, and 6 pi electrons. Yes, that is one of our Huckel numbers, and so we say 6 pi electrons, flat, ring-shaped. Yes, it's aromatic. Our last one over here, we start thinking about, well, what's going on? We do have a carbon with a positive charge, which is not super, stable anyway, but that means it has 1 hydrogen on it. This carbon must have 2 hydrogens on it, and that's where we can stop, because what we see here is right there we've got an sp3 hybridized carbon. That means that we don't have overlapping p orbitals all the way around, so it is not aromatic. We don't even have to count up electrons because we are not even in the right structure for it to be aromatic. Okay. The last problem on the worksheet, 1734, asks us to go just a little bit more in depth, which I kind of was already doing up above, but we'll do a few more problems here. And again, many of these contain heteroatoms. For all of those heteroatoms, you'll want to draw in your lone pairs of electrons. You'll want to consider, well, what must be the case? And again, let's do it this way. So if the oxygen is sp3 hybridized, which we'd imagine it would be, because it has 4 electron groups around it, if it's sp3 hybridized, well, that breaks the aromaticity. And we'd have to say it's not aromatic. Okay, so I'll say if. On the other hand, if the oxygen was sp2 hybridized, then we've got 8 electrons, 4 pairs in our pi system. 8 pi electrons is anti-aromatic. And remember, anti-aromatic is this high energy, super unstable state. And so if the molecule gets a choice, right, and we want to give it some feelings, it would prefer to occupy the lower energy conformation. And that comes with oxygen in the sp3 hybridized state. And we would just say it's not aromatic. That's the lesser of two evils here. Okay. Part B, let's look at this one. We could do the same kind of a logic here because we have that nitrogen. We know the nitrogen ought to be sp3. And so if it's sp3 hybridized, then that pair of electrons would not count. In fact, the structure, the shape would be wrong. And so we would have to say, if it's sp3, it's not aromatic because the shape's wrong. If the nitrogen's sp2, well then our lone pair of electrons here would be in the p system because our bond has to be geometrically in the sp2 hybrid state. And so if that's the case, then again we get 8 pi electrons in that pi system. We'd say it's anti-aromatic. And again, that would be bad news. So the nitrogen here will adopt the sp3 configuration to give us the lesser of two evils, the lower energy state. It's not aromatic. Part C. Let's throw on a couple of lone pairs here. Nitrogen's got one, sulfur's got a couple pairs, just like an oxygen would, right? Don't get thrown off by the oxygen-sulfur thing. So when we look at this one, we'll do the same sort of a logic. We'll say the nitrogen already is sp2 hybridized. It's participating in a p orbital overlap with carbon in the form of that double bond. And so what we've got then is this is in the p system, as is that, or the pi system, I should say. This lone pair of electrons is sp2, so we're not going to worry about counting it. What about sulfur? Sulfur is either sp3 or sp2. And so we'll look at, can we get an advantage by it being one or the other? And we can. So this is similar to what we saw up above. If the sulfur is sp2 hybridized, then we get 1 pair of electrons to count into the pi system. That gives us 6 pi electrons, which is aromatic. So in this case, our choice is between aromatic if sulfur is sp2 and not aromatic if sulfur is sp3. In the preferred case there, the lower energy is aromatic. All right, when we look at D and we add in those lone pairs, each of these nitrogens looks like the nitrogen in the previous problem. So we know that the lone pairs on both nitrogens are in the hybrid orbital because they're already participating in p orbital overlaps. And so 6 pi electrons, that's aromatic. We look at part E over here. Okay, now the nitrogen has a positive charge. Well, it doesn't really matter, right? The previous nitrogen had the same kind of setup with a lone pair over here that wasn't bonded to anything. Now that lone pair is bonded to something, but we don't care. It's in a hybrid orbital. So our p orbital overlaps are still here, still 6 pi electrons, still aromatic. When we get to part F, now we're getting the hang of this. So let's say, there we go, 2 pairs of pi system overlapping orbitals anyway, so now 4 electrons. Oh, but wait a second, this nitrogen has 4 bonds to it. It has to be sp3. We can't talk about changing anything because the geometry is set by those 4 bonded atoms. So sp3 hybridized, it's not even worth counting anything else. This thing cannot be aromatic. Part G, even though that oxygen has a plus charge, don't forget that it still does have 1 pair of electrons. Right? A neutral oxygen would have 2 pairs of electrons. This one has 1 still. So again, the oxygen ought to be sp3 hybridized, but it has a pair of electrons. We could reconfigure it into the sp2 if that's beneficial. And so in this case it is, right? We have 2 electrons in each of the double bonds. That's 4 pi electrons. If these also contribute to the pi system by making it an sp2 hybridized oxygen, then we get 6 pi electrons, which is aromatic. And then this molecule, which I hope looks really odd to you. A very strange molecule. Here's the same kind of logic we used back in part 32C, where we said the only way for this thing to be aromatic, to even have a shot at it, is if it's flat. The only way for it to be flat is for both nitrogens to be sp2 hybridized. We have to have that to be flat. That'd be a really unstable molecule because of the geometry, but that's the only shot we have. So let's consider that. If both nitrogens are sp2, then that means we have our bonds are sp2 hybridized orbitals, and our lone pairs, both of them, right, both nitrogens, have to be in the p system, the pi system. If that's true, we've got 2, 4, 6 pi electrons, which is aromatic. Because we can get that extra stability, that aromatic system, by having both nitrogens sp2, that's the answer. If either nitrogen were sp3 hybridized, that would break that flat system. We would have a non-aromatic molecule. Not anti-aromatic, just not aromatic. Aromatic's lower in energy, that's going to be our choice. So what you want to do when you're looking at examples like this is to go through, again, and basically use this kind of logic to say, what are the choices? What are the 2 possible outcomes? Well, let's imagine the heteroatom being in one configuration, and let's imagine it being in the other one. And which one of those configurations is lower in energy? The lower energy one is the one you're going to pick. So if your choices are anti-aromatic, that's really bad. You're not going to pick that one. If you have a choice of aromatic, that's really good. Low energy, you'll pick that one. Sometimes you won't have a choice, as in the case where something is the wrong structure, like this one, and then you just say aromaticity doesn't even apply. We're not going to talk about it. So practice similar problems like this, both counting pi electrons as well as determining aromaticity, and work through some practice problems. Ask questions if you have them, and good luck.